the SAGA survey for dwarf satellites around Milky Way analogs, and specifically, I'll mention some general properties, but I'll specifically talk about one aspect of it that we haven't published yet. So SAGA was led by Marla Gia and Risa Wexler, whom I met at Santa Cruz. And what it is it's a spectroscopic survey for dwarf galaxies in the fields of Milky Way mass galaxies. So this is a picture of it. You can't see it very well, but this is a picture from Sloan. It's a degree-size field. In the center is an NGC galaxy that's about 30 megaparsecs away. And what we do is we take spectra of a lot of stuff in the field, and we find some satellites of it, which are the little postage stamps over on the right. And there are several papers, particularly led by Yao Yuan Mao and Marla Jiha, that have been published that give a lot of details of the survey and the full sample of the satellites. So that's the boring title. All right. Touch anything? I'm not sure if this window has the focus. There we go. All right, so the more out there title is a measurement of the spin parameter of Milky Way mass galaxy halos, and probably have never heard anyone say that because it's a little crazy. But that is what I'm going to talk about. So I don't read all of the text here, but what is SAGA? It is a survey to find dwarf satellites in the fields of Milky Way analogs. So the analogs were, so there's 101 of them. They were selected to be very similar in mass to the Milky Way and somewhat isolated. They turn out to be basically NGC galaxies at around 30 megaparsecs, which makes the virial radius about 250 kiloparsecs, about 30 arc minutes. We select candidates from wide field imaging data and then do wide field fiber spectroscopy to find we take a spectra of a few hundred objects and find on the order of 3 to 4 per host. There is a lot of scatter per host. I'll show that in a moment. So very similar to what we just saw with the ELVS and ELVS dwarf surveys. That scatter in host-to-host scatter, I believe, is very real. Why did we do this? Because there's been a ton of effort put into studying the Milky Way and M31 dwarf satellite systems, and we wanted to understand if those systems are typical, inferences from them, and we can draw inferences from them, or other systems might be different. What did we find? We have a catalog of 378 satellites in these 101 fields. That's down to a mass, which is the mass of roughly the Leo or sculptor dwarf spheroidal. So that's a somewhat higher mass than I think the sensitivity of ELVS. The galaxies that we're looking at are further away. They're spectroscopically detected dwarfs. So the number is similar to the Milky Way and M31, and now, things have progressed since 25 years ago. This is not generally considered a missing satellite problem. There is a lot of host-to-host scatter, and we do find about 75% of the dwarfs that we find are star-forming. That's not purely a selection effect. It suggests that the quenching of dwarf satellites is different in different halos. So the Milky Way and M31 are not completely representative in that respect. And there's a lot more detail in these papers, but yeah. So why do we need to do this? And basically, you don't have to read all the text, just look at the images. These are images from Sloan or legacy surveys. And the problem is that we're looking for objects that are at redshift 0.01. And something that is at redshift of 0.1 and is just somewhat brighter is essentially indistinguishable even after you do a color selection to find low Z galaxies and so on and so forth. So we have to go out and take spectra of them. So that's what we did. It took a lot of time. It really did take about 10 years from the time that we started the project to the time that we published papers 3 and 4. So, that's the problem. You can't do photo Zs at 0.008. Or you can, but you can't tell the difference between that and 0.3 or something like that, right? So, and this was all done with MMT hectospec and AAT AA omega thanks to generous allocations of time from places like Arizona, Noir Lab, and then the Risa and Marla were able to round up some funding with which we were able to purchase time on AAT. And the staff of the observatories were very helpful in getting this all completed. So I won't go over this in incredible detail, but on the left plot is a plot of the mass functions, the different, each line here is the mass function of satellites of a host. So there's 100 lines on the plot. And there is a lot of scatter. The average number is more or less as expected. There's a bunch of things that you can say about this, about the mass of the most massive satellite related to the number of satellites, and so on and so forth. On the right plot, this is going to be what I'm going to be talking about, is the relative velocity of the satellite versus the host. And here it's so that's the y-axis, and the x-axis is projected radius. And then there are some curves on there that have to do with what the velocity is that you expect for a dark matter halo of mass. I think it's either 10 to the 12 or 2 by 10 to the 12 in this plot, but something very reasonable for the Milky Way. So the green points here are the ones that are inside 300 kiloparsecs, and that's what we're calling satellites. So something that would be interesting to do is ask, what are the kinematics in the host galaxy frame? So we've got a bunch of, satellites on the sky and the hosts are all different directions. Most of them are spirals, some of them are ellipticals, most of them are rotating. But the problem is, if you want to put things in the host galaxy frame, you can measure the major and minor axis of the galaxy, but you'd really like to know which way it's going. And it's 2025, and we do not know which way every NGC galaxy is rotating. So if anyone tells you that galaxy evolution information is like we're done studying it, just remember that. So I did an extensive trawl through the literature. I was able to round up about 25 measurements of kinematics from existing IFU surveys, about 20 from the literature where somebody published a rotation curve of a galaxy in 1988 or whatever, and actually labeled the figure enough that you could tell, like, oh, the northeast side is coming towards us, because people don't always do that. And we took a bunch of spectra with the MMT to get rotation curves. So there's like 30 things that I know. So that's not complete yet, but we have 75 hosts with a good measurement of rotation direction. So that when you have a measurement of rotation direction, you know that the host is not utterly face on, right? There's some projected velocity. And 293 of our satellites are in those hosts. So now everything that I show you from now on is in this host frame where the z-axis is along the minor axis, and there's an approaching side and a receding side. And we can compare where the satellites are relative to that. And you've got a bunch of blue and red points here. And you can kind of see, I will demonstrate this statistically, that there are in fact more blue points on the left-hand side. So there's a little bit of an excess of satellites coming towards us on the side where the galaxy is coming towards us, and ditto going away. So there's a little bit of progradicity, but you don't see like any huge anisotropy. The satellites are not all in the plane of the disk galaxy. They're not all in the pole of the disk galaxy. I can't really say anything about, great planes of satellites, because here I've stacked up the satellites around 75 different hosts. We have already tested that in a different way by measuring angular separation. That's in one of the SAGA papers that's already published. Here, the cyan and magenta points are the velocity distribution and radius distributions of the prograde and retrograde satellites. And you shouldn't see anything here because, in fact, they're basically statistically indistinguishable. It would be interesting if, like, all the prograde satellites were further out and the retrograde satellites were closer in or something like that. But we don't find any signal of that. Here I've got the velocity distribution as a function of radial velocity. So prograde is positive, retrograde is negative. There's a velocity histogram. There's a lot of spread because there's a lot of both progrades and retrogrades. And on the right-hand plot, I have plotted the specific angular momentum. So that is the radial velocity, times the distance along essentially something parallel to the major axis. So that's the specific, and it's just it's not got the mass in it. If you put the mass in it, then everything winds up being dominated by the few most massive satellites. So this specific angular momentum is a theoretically very well-studied quantity for dark matter halos and so on and so forth. And I have also divided the sample into star forming versus quenched. There's not a ton of difference here. The only real difference with the star forming versus quenched is something that we've already published, which is that the quenched satellites tend to be closer in, but not a difference in specific angular momentum impact from that. So what we find is that the prograde fraction is about 55% with an error bar of 0.03, so that's like a 1.6 sigma detection, not terribly impressive. I will get into why you should still care. And there is one previous study which used just pairs of satellite and isolated host that found a similar number with a similar error bar. But that's back in 2008, work by Stefan Herbert Fort, who was actually an undergraduate here. So, is this significant? Does it mean anything? And I did a statistical test, actually 2 statistical tests to ask this question. So I took the specific angular momentum, I summed it up for the satellites, I found some number that is a little bit positive, and then I did 2 things here, which is the left plot, I bootstrap resampled the satellites, and on the right plot, I sign flipped the velocities, and I generated realizations, with random sign flips, drawing satellites from the real distribution of radial velocities, but with the sign flip and projected distances. And so the bootstrap resample gives you a statistical measure. This histogram gives you a statistical measure of, the uncertainty on the specific angular momentum, and it is, displaced from 0. And then in this right-hand plot with the sign reversing, you get a histogram that's centered about 0, which you have to, right? Because you're modeling it as if you're drawing from a distribution with 0 total. And then we see that the measurement is kind of out towards the edge of the histogram. So it is meaningful. Both of these basically say that it's a 95% confidence detection, which is not great. That basically agrees with the 1.6 sigma. So it's not super significant. It's small detection of progradicity, but it's there. So what the heck does that mean? Galaxies and halos acquire spin from tidal torques. The aggregate kinematics of the SAGA satellites, because it's the whole thing. It's not just one satellite, but the whole thing. Probe the kinematics of the galaxy halo. The median radius of these that I'm using here is about 160 kiloparsecs. They're pretty far out. It's the kinematics of the halo relative to the orientation of accumulated angular momentum that winds up in the central galaxy, because that's what I'm using to define the reference frame, because I can't actually see the dark halo. So we don't know for certain if the current satellites are a fair probe of the entire dark matter halo, but they are at pretty large radius, so it's at least interesting. Another thing about CDM is that dark matter halos acquire spin. They have a spin parameter. That spin parameter, if you put it in these specific angular momentum terms, it's the angular momentum divided by the mass, divided by a couple of a radius and velocity that make it dimensionless. So this is a very well-studied theoretical quantity. It's called lambda. The typical lambda dark matter for dark matter halos in CM, there's a paper by somebody named James Bullock that has measured it for large, it's usually about 0.3 to, it's sort of 0.3 to 0.5. And the 0.03 to 0.05, it's quite small. Halos don't rotate super fast. And the interesting thing about the spin parameters is it's really not dependent on stuff. It's not dependent on halo mass. I don't think it's very dependent on formation time. In fact, I think it's a little understudied because it's not dependent on things. So you might ask, what did I measure for the satellites? And this is a little shocking, but it is 0.031. Plus minus 0.02, because this is a 1.6 sigma measurement, as I said. So we found a weak but coherent alignment of the outer halo spin with the central galaxy. And it's weak, but it should be weak. If I had measured 20%, we would be in deep doo-doo, right? Because this halo spin parameter, the fact that it is small and positive, thank you. It's a fundamental prediction of CDM galaxy formation. I don't think it's incredibly well studied what you expect to find from measuring dwarf satellites this way. And I think that 20 years ago, cosmological simulations were probably not at the point where you could believe the dwarf satellite formation and go and measure this thing. I think that probably they are now, at least, because you're talking about things that are not incredibly influenced by interaction with the central. So I think people should be going out and saying, what in fact do you find if you look at a simulation? Of course, we are going to look at that. So we do need, I think, more theoretical study to model if the satellite system should be a fair measurement of the spin of the dark matter halo. And then the other thing that I want to mention, I don't want to spend a lot of time talking about alternative theories, is if models other than CDM predict some other spin parameter, and I'll tell you that I think if you were to go way far away from CDM, if you went to one of those all baryon alternative gravity theories, I mean, I would assume it would be different. I just don't know how it would be different. So that's all. This is the last slide. I'll be happy to take any questions.
Question. Frank?
So this is bold and interesting.
You can say it's nuts.
Huh?
You can say it's nuts.
No. I think it's great. I mean, there's two things. I'm trying to do a projection in my head, but in principle what you measured is a projected separation and a line of sight velocity, and so you don't really have measured JZ.
That's correct. It's JZ projected, and there's this factor of a square root of 2 or 1 over square root of 3 or something like that, which I did put in the measurement of the spin parameter. I think what would be fascinating is if you were to divide, so I've tried doing something like dividing the sample into hosts that are more elongated, so they're more edge-on. And it turns out that you get roughly the same measurement, because what happens is I think you get a slightly stronger signal, but you have fewer galaxies in your sample. So statistically, it winds up being roughly the same. But what would be really amazing is if you could do this for a lot of things, and then you could take the face-on and edge-on separately, and you could model the distribution function of satellite velocities. That would really tell you, I think, an enormous amount about the satellite system kinematics.
I mean,
but with this sample, there's just not enough.
So related to this, we've done this with Sloan, with satellite galaxies, and many systems. There's a clear indication that satellites preferentially lie along the major axes of the galaxies,
right.
And so. But you said that you guys don't see this sort of alignment effect.
Well, I didn't. I mean, I showed you the plot. I did not measure the plot, but it doesn't look like there's anything. One of the things is that this is a very highly controlled selection, because we, went out and we selected the centrals to be, not have more massive neighbors, and then we selected the satellites in a very controlled way. And something that the papers that have looked at satellite distribution have said is that you really have to be ultra careful with how you select the centrals and the satellites if you're just taking them from Sloan in order to measure that. So I don't know what the answer to that is. I suspect that it has something to do with the separations and masses of the satellites in those papers. I don't really know. Yeah, but it is interesting because, as Frank was saying, there are some measurements of where you expect to find satellites that they're more. Yeah, I think that's LMC mass satellites, basically.
Satellites are a good tracer of the shape of the halo, and if galaxies line up with their host halo, then you would expect such an effect, and that's sort of how it's.
Yeah, sure. Yeah, I also wonder about sort of shape of halo or preferential direction of accretion. Is accretion coming this way or that way? Those are probably the same thing, I guess.
Okay. I think Andrew asked.
Yeah, I guess it was similar to Frank's question, which is if I give up on any expectations on alignment with the central disk, and you just use the projected measurements, but basically ask a similar question, do you get, in terms of the coherence and the spin of the orbits, you get the same answer? Did you test that?
The problem is that then I don't know what axis. So I had to, in order to put everything into the same frame, I had to use the position angle of the central because, you know, they're all different directions on the sky, right? So I have to rotate them all to have the same x and z axis.
But I think
and
you
for
could
that,
just-
I use the ellipticity of the central. So.
But you have the mechanism to do I'm assuming you're doing projection on top of some underlying dynamical model, so you can just ask for random projections, is it consistent with the line of sight angular momentum distributions you measure?
I'm not sure.
Because I'm just saying I could imagine a scenario where there's net spin, but it just doesn't align itself with the central galaxy, and I'm trying to imagine a way that you could actually test that.
Yeah, so, well.
That's a strong assumption that I should expect it to align with the central disk.
Yes. I mean, I could take the sample that we have and I could construct a histogram like this without aligning it with the central disk and see what happened. And, you know, I'm pretty sure that you're going to get 0 because it's the question, it's like there was a small prograde versus retrograde asymmetry, which is where this is coming from. And if you randomly orient the axis about which you're determining prograde, retrograde, I think it's just going to wind up being 0. Sandy
I
has a
think
question.
James has. You can go, Sandy.
Multiple dwarfs in them. Look for correlations.
Well, so what we did with because, you know, there's been a lot of noise made about great planes of satellites. And what Yao did in one of the previous SAGA papers was that he looked for places where, like, what's the angular distribution of the satellites around the central relative to each other? Do you see an excess at 0 or an excess at 180 where the satellites tend to be aligned? And it turns out that there is no statistical excess, and I don't think that there's a co-rotation signal. I'd have to look at the plot again. But.
James?
So just a quick question, Ben. You sort of flashed it. Was there no difference between the quenched and the non-quenched satellites if you broke them up?
We'll see if I can go back. So here, for example, there's the quenched and the quenched are black and the star forming are green, and the total is a blue dashed line that you probably can't see. The thing is that so there's not much of a difference, and because the quenched are only about 25% of the sample, they become hard to measure.
Yeah.
The major difference is that the quenched satellites are at lower radius.
Right.
And so that influences, it's a little bit hard to separate that from whatever influence it have on the magnitude of the specific angular momentum is smaller for them because they tend to have about the same velocity as dispersion, but they're at smaller radius.
Where I was going, and I know that, maybe not enough data, but subhalos that are accreted earlier tend to have less energy than subhalos that were accreted late. And my guess is this would show up in this way if you're normalizing by the total virial radius and not at the virial radius at time of accretion. So eventually there could be a signal there, and my guess is that would be a way of sort of learning if accretion time had something to do with this quenching mechanism and stuff like that.
Yeah.
I know that you're probably a long way from that, but it's, anyway, really cool.
Yeah, I think there's some, yeah, the fact that the radial distributions of the quenched and the star forming are really very statistically significantly different. We discussed that in SAGA papers, but perhaps didn't emphasize it enough. And there's got to be something there about, I don't know whether it's quenching or dynamical friction or something like that. But I feel like we could go further with this, but we need a much larger sample. Right.
Yeah.
Yeah, cool.
So, okay, this is very interesting, but we should move on to the next speaker.
Yeah.